kind of didn't get it set up in time. So instead, we're going to try to do this just by drawing pictures. And then what we'll do is we'll draw, we'll use a graphing program to draw the pictures there. And then we'll see how the whole idea of the tangent plane is going to look like. Linear approximations and differentials also would be some of the things that we might have seen in Calc 1. So let's find parallels or analogies or analogs from Calc 1. So from first semester calculus, we studied derivatives, and once we studied derivatives, we kind of came up with the formula for a tangent plane. And the formula for the tangent plane that we came up with was, so this is, first of all, this is our usual function y is equal to f of x at the point x equals, sometimes we use x naught, sometimes we use a. Should we use a? Let's use a. And so we came up with a formula for a tangent line, y minus y1 is equal to the slope, m is equal to x minus x1, but we saw that the slope was equal to the derivative, and the y1, if we're having this at x is equal to a, the y value would be what? You remember? F of a. So this is the m part, which is a slope, the derivative evaluated at a, and then x minus a. If you look at this closely, and if you try to remember Calc 2, this is, I can add more terms here, the second order, the third order, and stuff. Does that remind you of anything? Does that look familiar? Series, more specifically Taylor's, Taylor series for the expansion of the Taylor expansion for a function. And if you stop the Taylor expansion of the function at the first derivative, then you're looking at the linear approximation. And then if you keep going, then you're looking at the quadratic approximation, the cubic approximation. So you're looking at tangent lines, tangent parabolas, tangent cubic functions, and all that stuff. And the idea is that to look at this as the tangent line. And then from the tangent line, they have a linear approximation, which is essentially the tangent line. And then really they just call it L of x. And then it's really the same formula. And then the differential is going to be sometimes denoted as dy. And this is really just the without the f of a portion. It's really just the derivative of the function times the change in x, which is this delta x. Well, the delta becomes a d. And then yeah, so all this comes from this idea of this formula, the y minus f of a business over here is like the change in y, and that's equal to f prime times the change in x. And then the differential just takes it to like those infinitesimally small changes, and so it becomes dy and then dx. And then if you look at this Leibniz notation, if we abuse Leibniz notation a little bit, we have dy over dx is equal to f prime of x, and that's just one of the ways that we saw it back in Calc 1. All right, so this is the general setup that we have in the past, and now we're going to regenerate a slightly different looking formula when we're dealing with a new function from R2 to R. So let's start with that. So now we're going to consider a new function, and we'll start with R2 to R, and then instead of rehashing it out from R3 to R, then we'll just take a look at the obvious extensions, the extensions. So what we're going to do is we're going to take a look at it, and then we're going to approach it from a graphical point of view as well, so that we can get a nice picture of this in our heads. I mean, after all, we're talking about the tangent plane, and so there's geometry involved there. So we'll start by saying that we have a function z is equal to f of xy, and then we have some point on the xy plane, some point in the domain. In the Calc 1 analogy, it was A, but here it's the input is actually a two-dimensional point, so we'll call it A comma B. And then, of course, we have the point in 3 dimensions that we would be interested in, and that would be A comma B comma f of AB. So that's the point being put into the function, and we're getting a z value. All right, what we're going to do is we're going to consider the partial derivatives separately, and then we're going to take a look at how these partial derivatives make up a tangent vector. All right. By the way, what do we need for an equation of a plane? We need a point and a what? Normal. Okay, not a direction is for the line, normal is for the plane. So we need a point and a normal. And do we have either of those so far? So before we even get started, we got the point already. We're like halfway there. Well, 1 out of 2, right? We're not quite halfway there. We're like 1/10 of the way there. Because the other half, the direction, is going to be a little bit more difficult to find. So the idea is that we want to find a normal vector. And we're going to do this by finding 2 vectors that are on the plane. And the 2 vectors that are on the plane are going to be tangent to the surface. And then by finding the 2 vectors that are on the plane, how would you find the normal? You would cross them, and then we get a vector that's perpendicular to those 2. So that's our plan. All right, we good with the plan? All right, let's do this. First, let's consider the derivative with respect to x or with respect to y. So, I don't know, which one should we do first? Let's do a derivative with respect to x. So we're going to hold y fixed. We're going to cut this with a plane. So we're going to cut it with a plane y is equal to b. So the plane y is equal to b gives you a y value of b. So it has to cut through this, and then it's going to cut through this at some sort of path. You see that cut, that slice? So it's going to cut through it with this path. And what I was interested in doing is I was interested in taking a look at this just from a two-dimensional perspective. So I'm going to rotate the view so that I'm actually looking at that plane as if it was a flat-looking plane. This is a plane y is equal to b. And so if I'm looking at this as a flat-looking plane, what are the two axes that I would be looking at here? The x and the z-axis, right? So I'm looking at my x and the z-axis. And I'm attempting to draw this path over here. So it kind of looks like that, maybe. And this is my point. This is my x-axis, so this is the point x is equal to a at this point right here. So this point a comma b comma f of ab is this point over here where y is equal to b. But I'm looking at it two-dimensionally, so I know that my y is going to equal to b. So if I'm looking at my xz plane, the two-dimensional point that I would be looking at would be a comma f of ab, which is like my z component. So I'm just looking at my xz component there, because my y component is b. Now, yesterday, or whenever we did partial derivatives, we computed partial derivatives. And what we saw was that we can find the derivative with respect to x. So given this context, what is my derivative with respect to x in this picture? What's your derivative in two dimensions? Back in calculus, what's your derivative in terms of your geometry? Be more specific. Slope? It's the slope of the tangent line, right? So if I were to draw a tangent line, say right here, then the derivative with respect to x is going to be the slope of tangent line. So I want to be specific here. This is fx and specifically evaluated at a comma b, because if I evaluate that at different points, then I'm going to have different answers. So I'm close. I have this line right here. What do I want again? What did I say I wanted? I wanted to find a normal. I'm backtracking. How do I find a normal? I take the cross of two vectors. So it looks like I want to make a vector out of this line here, right? So I want to make a vector out of this line. So I'm going to go back to the two-dimensional picture and say I want a vector out of this line. Now, how am I going to find a vector out of that line? What is this vector going to be? For a vector, I need components. I need an x component, a y component, and a z component. Now, let's take a look at this vector. And can you give me either any of the components, either x or y or z, based on the picture, the two-dimensional picture and or the three-dimensional picture? What about y? Close. Y is always b, right? What's that say about the vector? It's on the plane xz. It's always what? Are we all thinking here? Always parallel to the xz plane, right? It's on the xz plane. What can you tell me about the vector? I'll call it v sub x. Maybe I might need more room here. What can you tell me about the y component of this vector that is always parallel to the xz plane? Is it b? No. Is it what? Is it 0? Yes. Why is it 0? Because it's what? It's flat. It doesn't move along the y, right? It's on the xz plane. It's parallel to the xz plane. It doesn't make any movements. So this v sub x vector that I've called v sub x is a vector that describes that tangent vector. So it's tangent to the surface at that point. It's going in the direction of x. And it's on this plane, y is equal to b. On that plane, y is equal to b. That means it's parallel to the xz plane. And there's no movement in the y component.
So vectors like tangent, but has the same slope.
It has the same slope as this tangent line. Okay? All right. I like to think that was the easy part. So, to find the other two components, now we're on the xz plane and we're looking for the x and z components. So we want to know what the movement is along the x and the z component. So what I'm going to do is I'm going to take a look at this purple line again, or the green vector, it doesn't matter. We could take a look at either of those two vectors, and I'm going to make a rise over run triangle for this vector. And what's the rise over run when you think of rise? But let's go back to algebra. When you think of rise over run, what do you think of? Slope. Y2 minus Y1 on top, X2 minus X1 on the bottom. So, but essentially slope. Slope is what I was looking for. We know the slope, right? Slope is Fx, right? So we want to do a rise over run to write it or to express it as a slope. So if we look at this, though, the run is going to be the x component, and the rise is going to be the z component. And that's exactly what we're looking for, right? The change in x and the change in z. Now, we want rise over run to equal fx. What can we say about the rise or the run?
The run is x minus a. I mean, x minus a. We can think about it as x minus a.
Can we think about it a slightly different way? Can I assign values to rise and run? Like what values can I assign to rise or run? Okay. Yeah. What if I say x over y is equal to 5? What should I let my x equal, and what should I let my y equal? What? Your x is equal to 5y? Yeah, I want actual values for x and actual values for y. 10 over 2? So x can be 10, y can be 2. Is there another 5 over 1? So if I let x equal to 5 and y equal to 1, then that'll work. Okay, so that's what I was hoping for. This rise over run is equal to this number. Now, this is just a number, right? fx, and you put in the x value, the a value, and the a for x and the b for y, then you're just going to get a number out of that. So this is just a number. And I want a value for my rise and run. Backwards. So if I just want values for rise over run, and I know what rise over run is equal to, why not let run equal to 1? Right? If you let the run equal to 1, what's the rise going to be? fx. So that's what we would like to do. That's what I would like to do. I would like to put 1 in for the rise, or I'm sorry, the 1 for the run, and the rise is going to be fx. I'll say fx, but I'll write fx of a comma b because I want to keep stressing the fact that you're putting in a value for x and y. Now we have a vector, one vector that's tangent to the surface at that point. Wait, hold on. Wait, hold on. I'm answering your question. What was that? Why is it 1? Because we have a choice to put a number for rise and run. We know that this is equal to fx. So if I make the run equal to 1, then my rise is going to be whatever. If I make the run equal to 2, which is possible, then my rise is going to be 2 times that. Yeah. There was another question? Comment? Yeah, okay. Yeah, we're going to find another vector, yeah. Well, yes, it's going to be. Okay? You guys are jumping. You guys are, yeah, spoiling. You guys are stealing my thunder now. Okay? So, we're going to do the same thing. Should I go faster now that somebody just told me what the answer was? So, I would redraw the whole thing, except this time I would redraw it going along the y. So I would fix my a, or fix my x equals a, and then I would slice it with a plane and come up with another graph. Then I would take a look at that flat on this plane, x is equal to a. This time I have my yz parallel to the yz axis, or yz plane. And this time my y is equal to b because my x is equal to a already given. and then I'll get a piece of that surface where I'm just looking at the curve. At my point A is understood, that's my x value, but flat on the yz plane, I'm looking at b comma f of AB. So I get the same picture, right? We get the line with a specific slope. This time it's running along the y-axis where x is fixed. So my slope is going to be f sub y, the partial derivative of f with respect to y. And then I would create my v sub y vector. And that vector is not moving along the x-axis, so it's fixed along the x-axis. And then if we do that rise over run business on the y and the z again, if we make the run equal to 1 in the y, then my rise will be the slope in the z. So let's just add on the other components that we have. So that went a little quicker. All right. So, ready to put it together? Let's get this. Let's put the two vectors in here. We had a vector going along the y, and then we had another vector going along the x, and they're both tangent to the surface. So let's remember those vectors again. I think the first one was Vx, and that was 1, 0, Fx. The next one was Vy, 0, 1, Fy. So we're interested in crossing them. Here's a question. Does it matter which way we cross them? So what's going to happen if we cross it differently? It's negative or positive, right? So if we cross it one way, it's going to be pointing up, or if we cross it the other way, it's going to be pointing down. So which way should we cross them?
Fx cross Fy.
Or Vx?
Sorry, yeah.
So let's get a normal vector that we're looking for. Let's do Vx cross Vy. So Vx is 1, 0, Fx. Vy is 0, 1, Fy. And let's cross them. So in the I direction, it's going to be
Negative fx.
negative fx. In the j direction, it's a built-in negative, and then the j,
Negative fy.
negative fy. And then in the k direction, positive 1. So we got it pointing up, and in right-hand rule on this picture, you see that it actually would be pointing up. Because it's a negative in the j direction, and this is going to be fy minus 0. So it'll be fy minus 0, but it has a built-in negative to begin with. Yeah.
And then you can do negative fx. Sorry.
No, hold on. Let's savor this for a minute. Any questions so far? It, right. So the planes that we cut it with, right, because these things are not these two vectors are not like just going straight ahead. They're at an angle also. Okay. All right. So we have a point and we have a normal. What was our point again? And we have a normal vector, and so we're ready to put this together. We'll do it here. So the plane, how do we do it? We do the dot product. So it's fx evaluated at AB, and then times x. Can I do it the x minus a or whatever? Do you guys remember the other? So there's a few different ways to write the equation of a plane if you have a point and a normal, and this is one of them. You have a parentheses x minus x naught, b y minus y naught, c z minus z naught equal to 0. You can do the dot product, and you get the d on the other side by dotting the point and normal, but in either case, this is what you would get. I do want to solve for z to get z by itself, and to do that, these two terms would go on the other side and become positive, and then I would need to bring this term over to the other side, and that too will become positive. So let's take a look at the one version of the tangent plane here. Z is equal to f of AB. That's this last thing that we would have brought over to the other side. And then these other two terms would have been positive. And then this is what we have. Now, if you look at this and kind of compare it to the tangent plane or the first order Taylor polynomial from Calc 2, because we have two derivatives, two partial derivatives, where our linear term kind of got split up like this, right? But it's essentially the original function plus the derivative times x minus a, or whatever it was back then. So here's the equation of the tangent plane. Okay. So now let's take a look at the linear approximation and the differential. Once we have the tangent plane, everything else is kind of following. Linear approximation. We have, just instead of calling it z, it's going to be a new function. Instead of Lx like it was back then, now it's called Lx comma y because there's two variables. And we're essentially writing the same thing. F of a, b is a number that you would get if you put a comma b into the function. And here we have a derivative evaluated at a point. And then the other partial derivative evaluated at a point. And then the differential is similarly defined. Our z is our dependent variable, so we're going to represent this differential with a dz. And if you remember, it's just the height component that got taken out. So we have fx, and then I'll keep the xy here to keep it general. And then the delta, or the dx, the change in x, plus the derivative with respect to y times the change in y. Okay? Let's do a quick example and try to do a picture of it. And let's do a simple example with like maybe a saddle. That seems like an easy graph. So if we take a look at this, let's do it at a point. Let's pick a like 1, -2 or something. So what is f evaluated at 1, -2? This is going to be our z component. -3? So 1 minus 4, -3. And we need a couple more things. We need the derivative with respect to x. Fx is what? 2x. So fx evaluated at the point 1, -2 is 2. Fy is -2y. Fy evaluated at 1, -2. +4? Okay, we're done. Our equation of the line is going to be z is equal to -3 plus 2 times x minus 1, that's fx, plus 4 times y minus -2. And then that's your equation of the line. Let's see a graph of it. I started to graph it. I have A is equal to 1, B is equal to -2. And then our plane is that Z equals -3 -3 +2. Oh, come on. +2 times x minus 1 +4 times y +2. Oh, this is a -3. So if we look at it, it looks pretty tangent. Can you tell? So I tried to put that point. It looks like it's tangent. I could try to change the. I'm afraid if I change this, though, it might lose its. It might not look so tangent anymore. But let's see if I can change it to 8. 8. That didn't help. Well, it looks tangent, doesn't it? All right, so now we know how to find tangent planes, and then we could do linear approximations and differentials, and try to think back to your Calculus 1 differentials business to try to answer some of the questions in the homework. So the homework for 14.4, this is 14.4. It's set as due this Sunday, but I'm going to postpone it till next Sunday. So you just have some 14.1, 2, and 3 due this Sunday. You also have a couple of labs that got pushed back to Sunday as well, so keep an eye on that. Yeah, so that got extended. The test.